of attributes are binary because it's yes, no, on, off, and male, female. Computer science are very good if everything is binary because the whole underneath is built by a binary math. But I want you to pay attention to this so-called asymmetric attribute. Could it be binary? Could it be other digital, not binary? But what's asymmetric mean? Because you really need to look at examples. If you consider the data record a list of cancer patients, there's only two types. This is the chemotherapy. There's people take that therapy. People does not take the therapy. But if one of the people does not take the therapy, it's not really your concern. You only look at those who take the therapy. So that's asymmetric. When you deal with terrorists, let's say you tracked a lot of suspected ethnic group. But along this ethnic group, there's only a very tiny fraction that really could be suspected in a way, and then your data will be very asymmetric. Look at this, present or not present in some event. So you need to understand that this thing is not a symmetry. It's not just like a binary. Present and not present, or in another way, sometimes the data 0 mean nothing. Only thing is not 0. It's what matters. So we really later on deal with the case. We can discuss more. So far, what we talked is about the attributes. What you need to pay attention. Because before you do any analysis, your first question is, what type of attributes is going to help me to make the decision? And the candidates, you need to take it out. Once you take it out, you find that those attributes are so different. You look at it numerically, sometimes it's just qualitative, sometimes descriptive, and how you're going to merge them together to make your decision. And that's explained the part of the failure in the early days of the neural network. Because when neural network connected all those from the input to the output, people cannot trace in the middle. The weight, how much decisions weighted on what, because people cannot get the insight in how the decisions made. They're all mixed in the mind, and that's not as good as promised in the beginning. That's the non-linear behavior. Really screwed up everything. So they also deal with this asymmetric data, like those huge data, big caps of money and small tenure, and how many years the CEO worked, and how many times the committee member and the board of trustee changed, and those data. It's hard to deal. Now, understand the attribute is all about your design of the model. But now let's look backward to what you get, the data set characteristic. And you start from what you have and hope to achieve what you want to get. So we need to now start to know what kind of data I can get. And how do you distinguish those kind of problems? How do I judge? How hard is your question? And it really depends on what kind of data you get, what kind of result, how long distance is from there. So the characteristic is first, dimensionality. Do you know natural language processing is one of the most successful data mining thing? In the language processing, we got the documents. How the computer compare two documents In the beginning, they had a lot of linguistics and a lot of theories. In the end, they said none of those work, all break. The only thing work is the count. The statistician win all the battles in the natural language processing. How they do it? They just get a document, pick up those weird words, and they count the frequencies. And this is a vector. So if you look in the newspaper, each newspaper you are talking about the word net, 100,000 of words, there's a lot of weird words. You can try to monitor it in different fields. And your dimension is a vector. How many words you want to pick? If you pick 500 words, your dimension is 500 dimensional. That's the curse of dimensionality. You know, your vector is the frequency. This word comes how many times? And you know this thing is called turned in. Is the way to check if somebody cheat, the essay. How they do it? Easy. They have a database about all these famous good essay there, and the database have all these weird words, how many times they have, how many frequencies. If the viewers come to seminar, use the same words with the same frequencies, with the same lines, you know, they're gonna doubt that this is cheating. And the natural language is the same. They look at some words in how many frequencies, what a sequence. And the first thing is dimensionality. If you have too many dimensions, it always narrow down to the choice of you have. Understand that? The second one is the sparsity. The sparsity is like medical data. If you want to look at some leukemia patient or some kind of Alzheimer patient to respond to what kind of medicine, not only the data is very expensive, but a lot of zeros, because the people are different. They have this medicine and they don't have, and that's very messy. That's why that's another challenge. Sparsity. You don't have enough data, and even you have the data, it's a lot of zeros. That's when I talked about the asymmetric attributes. You get a bunch of this zero, you start your headache. This is how I can get the information out. Well, the third one, of course, the quality. The quality. What means a good quality data? What means bad quality data? I'm going to talk more later. The last one, the resolution. Talk about the resolution. I had my sabbatical. My project is to do a simple thing. Look at the satellite imager along the whole Indiana River Lagoon. That's 251 kilometers long. Average 4 kilometers wide. That's the lagoon you see, Mosquito Lagoon, Banana Lagoon, and all those things. We got this image, very poor resolution. 1 pixel will cover like 1 square kilometer. And then you try to decide if that in green color you see it's a seagrass or it's algae. And if you see that little yellow, is that the sandbar or some kind of dyed grass? And then we could do a lot of data fusion. We put some high resolution data, but very rare, a few sites. One is the in situ data, you get it from the bottom of the ocean, the picture, that could be 10 to the 6 power, more 6 magnitude, more high resolution, you know. And then you get the middle level, you could get airplane pictures, you know, aerial images. And then you do a fusion, try to use the high resolution, but the rare, small sample size to validate, to training, to test this high resolution model. So the resolution is very important in this case. Quality. Well, when people do signal processing, you always think about the noise. And the first thing is the signal-noise ratio. And that ratio will tell you the quality, make the job easy or hard. And artifacts. And sometimes for the image identification, you try to identify the enemy tank and on the area. It really depends on other artifacts that make it look like similar with that. It's very different for you to do the project in the desert or you do the project in the rainforest. So the artifact is one thing make this issue very difficult. And then the equipment limitation. For example, satellite imager and the error imager, or I use my AUV image. They're all limited. If the high resolution, they can kind of broad the whole globe, you can get it very quickly, and like Google. But if you get this AUV, you get a very high resolution, very accurate, but they only get a few spots, 30 spots. And you need to know what's the middle way, or how you're going to do the fusion. And the bottom line is you want to find the truth. The next, the procedure. When you don't follow anybody learned the statistical experiment design, you know the word random. How do you control the group? And you need to make this procedure be really scientific. Well, people say the data, that's not a lie, but the human do. You know, those politics data, you need to, first, to me, it's not about the data, it's about who collected it. The conservative group or the liberal group. And they already printed the color. Even they all follow the scientific method. They kind of put in the different people. You have the bias, and you have the accuracy. Sometimes not controlled, really the survey question. Sometimes the purpose for the misleading the people to the answer they want, and in those things. And the completeness. Did you have all set? Did you say, oh, I have a big enough data. I covered the 2,000 of polling result, but that your 2,000 that covered all different diversified group. That completeness is important. You cannot train the computer to know the new knowledge unless you give all the representative of the knowledge in your training. That's the completeness. If you don't get any data from the Asia group, let's say that minority, and then you cannot expect your trained model to identify any proper response from the Asia group. That's it. They have to learn from example, right? The completeness is important too. So understand that those are the quality control. Well, garbage in, garbage out. If you don't control the quality, you won't get good result. And then, how to handle the data. There's outliers. The outliers, there are some kind of statistical analysis. They wanted to purposefully remove the outliers. But for some data mining problem, these outliers is exactly what you're looking for. For the buyer or for your product to the fund terrorists, right? So also, how you're going to deal with this missing and incomplete value. For example, medical record. A medical record, rarely you find a complete set, unless you pay multi-million dollars to do a controlled analysis. Those patients have no job, all follow you to take all those things. You get all those data really very sporadic, spicy. And what are you going to do? And this is why medical data is expensive. Those data mining is very, very lucrative. I say NIH, how much money they put in. Just to produce one cancer medicine now costs $1 billion. 80% of fail because they just failed in the first analysis, statistical analysis. And 80% fail, make it in one medicine from new cancer medicine over $1 billion. That's how expensive. Well, of course, we know everything have inaccuracy. That's what I told my last class. Taylor, you remember? I said, theoretical mathematician said, what's the right answer? Start from the right answer. Applied mathematician start to think about the error model. How you're going to minimize the error. You start to realize where is the error source could make it wrong, and how do you make it minimize this error and try to cancel out some error. That's the whole difference. So you, as an applied mathematician, first think about where the mistake could come from? Maybe where the error come from? Instead of what's the right answer? I tell you what, there's no right answer. You just have good answer. But it is a hard science. Why? Look at Netflix. They have those computations here with $1 million award with the winner. Can you beat a little bit about the matching of the moviegoer and the movie? Since it's been there for a long time. They always have those benchmark project there. And to see if you build a new algorithm, can you beat the other one? When I do many years ago, I did a project in boundary rating. And they said our current industry standard is about 65% accuracy. Whatever tool you use, if you can beat this 65% of accuracy benchmark, you'll be finished. But when I finished my AI project, don't mention 65. You cannot even beat the 65. It's hard. That is, you can start the soft, everything you say you can get something. But in the end, if you really get like a basketball in a competition with a good team, and then you know how much muscle you really have.